Hello everyone. So now let us move on to a very interesting concept, which will be useful throughout this course, because when you're going to understand even the characterization of carbon materials, when you're trying to understand the manufacturability, applications, everything, you will find certain types of carbon structures which are curved. So one example of the curved carbon structures is Buckminster Fullerenes that you already know. Curved means anything that has a curvature. It can be a completely spherical molecule, or it can be something in between. So it's not completely spherical, but let's say you have a certain bending. Okay, so these kind of structures are then known as the curved carbon structures. Why do they have this kind of curvature? And where does it all start? So we know everything starts from the hybridization, right? If there are hybrid orbitals, they take a tetrahedral kind of geometry. Then you have diamonds. If they take a planar kind of geometry, then you have your graphite-like structures, right? Now, what happens if they take some geometry in between the geometry of diamond and that of graphite? In that case, you have a certain angle which is neither that of the pyramid nor that of the planar structure. You have something in between. And that is what, when it happens to several such atoms which have similar hybridization, in that case, the overall geometry is the curved geometry, and that is what we call curved carbon structures. Okay. This type of geometry is a result of sp2+n hybridization, and that is what is the topic of our today's lecture. Okay, so hybridization, first of all, now you know for diamond and graphite, and we also previously talked about the orbitals. How do we determine that? Well, there are two methods. So one method is that you can derive the shapes of this is the standard thing. This is how we actually mathematically derive the shapes of the orbitals by solving the Schrodinger equation for hydrogen atom. So this is basically the quantum mechanical approach. That is how you know that this is the shape of the orbital. There are also methods of experimentally validating based on the chemical reactivity, for example, of a certain type of material. You can also validate these shapes of the orbitals, but they are quantum mechanically derived. That is number one. Now, in the case of manufacturing materials, what we can also do is we can back calculate the hybridization states based on the geometries of crystals. Okay, so this is something clear to us, that the crystal geometries are basically nothing but sort of large scale geometries that we have also at this hybridized molecular orbital level. Okay. So we know this for graphite and we know this for diamond, and if there is something in between, can we really back calculate the hybridization state? And if we do, then what is it? What are the values that we get? And this is what we are going to learn in this particular lecture. Okay, so we are going to use the method number 2. Okay, can we also do this quantum mechanically using the method number 1? Yes, but there we have to understand that again the number of orbitals is an integer number, but the probability of finding the electron in those orbitals can be a non-integer value. Okay, so this is exactly what I have written here. So we talked about this unhybridized p orbital in the case of graphite. So we have 3 orbitals that get hybridized and they participate in bonding. In the case of diamond, all 4 orbitals get hybridized, and they form 4 molecular orbitals which are then filled. Basically, there is a bonding taking place. All of these electrons participate in bonding and they do not remain free afterwards. They are not really interested in doing anything else because they have already paired up. They have formed a bond. So these are sigma bonds, and then that is how we have the sp3 type geometries or sp3 type crystals. But in the case of graphite, it becomes interesting. Now you have this unhybridized p orbital. What is interesting for us is to figure out what is the probability of finding the electron in that unhybridized p orbital. As such, if there is no other option for the electron, then that probability is going to be 1. But what if there is some option, if the electron can potentially also go somewhere else? In that case, the probability will be less than 1. That probability will be then not an integer number. And that is how you can get these fractional probabilities and therefore fractional hybridization states. So that would be the quantum mechanical approach based on this, this idea. You can also calculate the hybridization states, but what we are going to do, because as when we talk about materials in manufacturing aspects, it is easier for us to back calculate the hybridization from the crystal geometries, right? Because the crystal geometries are important for us. And also when we are performing manufacturing on any given material, these crystal geometries can also be observed at a larger scale. So for example, if you are polishing or cutting a diamond, the cutting patterns, the slip planes of diamonds will be according to the crystal structure. Similarly, when you have a graphite crystal, you know that these planes, the basal planes of graphite, we will in detail learn about the crystal structure of graphite. The planes of graphite can slide on top of each other. You have this layered structure. So you know now that these layers within themselves, the single layers, they are very strong. But when they are on top of each other, when they are stacked on top of each other, the bonding between them is not very strong. So this already gives you an idea of the bonding. So even if you did not know the material at crystalline level, even if crystal level, even if you did not know what type of hybridization it possesses, even in that case, just by observing the behavior of the material at the time of manufacturing, you can understand the type of hybridization it can have. So for us it is, as I said, easier to back calculate. So we are also going to often encounter carbon materials which are curved, Buckminster Fullerenes being the most common example. So we can also now back calculate the hybridization from there. Let's try to do it in this particular lecture. Okay, fine. So I will start with some example. Let's say we have 3 orbitals, hybrid orbitals, and then we have 4 electrons, right? These 3 orbitals are hybridized orbitals, so they all have the same level of energy. So basically these 4 electrons can choose to go into any of these 3 orbitals. So what will happen in this scenario? Okay, you have 4 electrons, 3 orbitals. 3 of these electrons will go into 3 orbitals first. And now these 3 orbitals are half filled. What happens to the 4th electron? Okay, this 4th electron, let's say, can go into one of these 3 orbitals which were half filled till now, and then gets paired up. What would be the probability of this event? 0.33, so 1 by 3. Okay, but this will actually not happen, because when we think of it theoretically, it can happen, but it will not happen in practice because of the fact that hybridization only takes place at the time of bonding, which means that there is another carbon atom nearby. That carbon atom will also have 3 sp2 type orbitals. Let's say this is an example of sp2 type orbital when I say 3 hybrid orbitals of the same energy level. So let's say these 2 atoms will come close together and they will form 3 sigma bonds, and that is how you'll have the pairing up of the molecular of the electrons in the molecular orbital, which means that the 4th electron, that cannot go into any of these 3 orbitals anymore. They already have completely filled they are completely filled with the electrons. They have the paired up electrons. Okay, so this particular scenario will not really take place if this is if we are talking about hybridization or hybrid orbitals. This could take place if this was not happening at the time of bonding. So if we were not talking about hybridized orbitals, in that case the 4th electron could have the probability of going and pairing up with 0.33, but that is not the scenario we are talking about. 3 hybrid orbitals. Okay, so this will not happen. Now the other possibility for the electron, the one and only possibility, is that it remains outside of these 3 bonding orbitals or bonding electrons. So now basically this electron remains in the unhybridized p orbital, if we have one. Okay, so if this is an example of sp2 type of
orbitals, then we do have one unhybridized p orbital. So now your remaining electron will have 100% probability of being found in that unhybridized electrons orbital. This is the scenario when it comes to graphite. So we are talking about perfect graphite. However, what happens if this electron can also potentially, occasionally, go to another neighboring orbital, another, let's say, unhybridized p orbital of another neighboring carbon atom, or if it can occasionally also go into the hybridized orbital, or it can basically occasionally change its position with another electron if there is a probability for this particular electron to go into another orbital, hybridized or unhybridized. In that case, the overall probability of that electron being found in the unhybridized orbital is not 1. It is less than 1. Okay, fine. So this kind of event can take place in some carbon materials when there are neighboring unhybridized orbitals available. So this is in fact what happens in most of the cases, and that is why we have this pi band and not just, the electron is not always localized to its parent atom. Okay, it is not always localized. It does interact with its nearest neighbors, and that is why it may have less than 100% probability of being found in its unhybridized p orbital of its parent atom. Okay. Now, whenever when we apply any kind of bias, electrical bias, or we apply any other kind of force also, then this electron, however, this electron is definitely not participating in bonding. So this electron can potentially move. That is why we call it a free electron. So yes, this electron is then available for electrical conductivity as long as it has a high enough probability of remaining free. Okay. It also can provide chemical reactivity and many other properties to the material. And this is, of course, this is a non-bonding electron. Okay. However, now, if you have a certain type of crystal structure in your carbon material, which has its geometry between the pyramidal geometry of diamond and the trigonal planar geometry of graphite. If you have something in between, in that case, the probability of finding the electron in the unhybridized p orbital is less than 1. It basically indicates that the probability is less than 1. Okay, because if you had the geometry like diamonds, in that case, you had 4 hybrid orbitals now. But in the case of geometry, when you have 3 hybrid orbitals, it is like graphite. In that case, you have one completely unhybridized orbital. Now, if you have something in between, that means your completely unhybridized orbital is also somewhere in between. It is between completely hybridized and completely unhybridized. So that orbital is also somewhere in between, which means the probability of finding the electron there is also somewhere in between. It is a non-integer number, and that is when we can back calculate the hybridization states. Okay, so in which type of structures will this happen? This will it happen to so now you should have something, as I mentioned, you don't have the pyramid. Let's say if I take the bottom part of the pyramid, this is how it looks, and the angle between these two sides is 109.5. In the case of graphite, it looks like this. So this is 180. If you have something in between, that is what we are discussing, and that is when you have the non-integer hybridization state. So sp2+n hybridization state. So I hope it will become more clear from the next couple of slides. Okay, so let us take the example of Buckminster Fullerene. So this is the very well known curved carbon structure. Okay,
and it contains 60 carbon atoms. So this is one big molecule which contains 60 carbon atoms. So this is something very special about carbon, that we have large sheet and chain-like molecules. And that why I'm saying this, because these 60 carbon atoms, they are not completely independent of each other. Because this is one large molecule, it means that these 60 carbon atoms are bonded to each other. And what is also interesting is that the unhybridized p orbital, although it is localized, although it belongs to each carbon atom, there is a probability that the electrons from the unhybridized electron orbital of one atom interact with that of the neighboring atom, and the neighboring one will interact with its next neighbor, and so on. And we also do not completely know for how long there is the influence of this interaction. So the nearest neighbor interaction, in the case of not just curved carbon structure, but also in the case of graphite and graphene, we don't know if the electron only participates with its next carbon atom, or let's say the next 2 carbon atoms, or next 5 carbon atoms. This is something only very recently we have tried to understand it for in the case of graphene, so single layer of graphite. Okay. What I'm trying to say here is that your 60 carbon atoms are not independent, and the unhybridized, the electron in the unhybridized orbital is definitely interacting with the other nearby orbitals as well. Okay, fine. Now, to start with, because we need to understand what kind of structure, if we want to back calculate the hybridization and so on, we first need to assume something about the about our molecule. So we assume that it has the sp2 type hybridization rather than sp3, because, well, number one, there is a free electron available, and also because there is a significant number of hexagons present. That means there is definitely there are some sp2 hybridized carbon atoms. Okay. In fact, that is the reason you will also often hear people will say that if you take a graphene sheet and you roll it up, it becomes a carbon nanotube, or if you make a football out of it, it becomes a fullerene. This is just for an easy representation. This is not completely true. You don't really take you cannot actually make a football from a sheet which contains only hexagons. In fact, as an exercise, you can even try to do that. You can actually look at a football and you will see that it has also a large number of pentagons. If you had only hexagons, then you will have a flat sheet. You cannot really make a completely spherical structure. You can provide a little bit of curvature perhaps, but you cannot make a sphere out of a structure which has only hexagons. Okay. Anyway, we are going to assume that we do have one unhybridized p orbital, and that is why we start with this sp2 assumption of hybridization. Okay. Fine, but now we know that the structure does contain some pentagons or some non-hexagonal structures. Otherwise, we will not have any curvature. Okay. Here I have described it with some images. So this is your pyramid. This is the sp3 hybridized structure. This is your diamond. This is your when you have no unpaired or unhybridized orbital available. Okay. But in the case of graphite, you have one unhybridized p orbital on top and bottom. That is what I have shown with the lines. And then you have 3 electrons that have participated in bonding. So that they are in your trigonal planar positions. Okay. Now, with these triangles, you also know, we learnt in the graphite lecture that we can also make hexagon. If 2 triangles they come close to each other, then we often have these hexagon kind of structures, and that is why we have all of these hexagons in your graphite-like structure. So here I have drawn one hexagon, and all of these lines, they indicate the unhybridized p orbital of all 6 carbon atoms which are present in that hexagon. Okay. Now we will talk about the curved carbon structures. So curved carbon structures will make some angle. So in the case of this hexagon in graphite, you will have a flat hexagon, but in the case of curved carbon structure, it will not be flat. There will be some angle. Okay. And here in this illustration, I have then drawn this kind of, I will show you where this angle belongs.
okay, you see that you have some sort of curvature. One more important thing before we go into this angle and so on is that when we talk about the curvature, we are assuming that this structure is a polyhedron structure and not a complete sphere. So you will see the lines that I have drawn here. It is like this and then this. It is not like a smooth transition. It's not a complete, smooth sphere. Okay. So let me give you an example of a 2D geometry of a similar type. If you have 3 lines, what do you make? A triangle. If you have 6 lines, you make a hexagon. If you have infinite lines, in that case you will get a circle, right? Infinite small lines. But if you don't have infinite lines, let's say you have 60 lines, in that case you will get the structure of a polyhedron which has 60 lines, but you can still have well defined separate 60 lines. Okay, so if now think of the same thing in 3D. Instead of a circle, now think of a sphere. So if we have these hexagon kind of structures, hexagons, pentagons, if you had infinite number of those structures, then you had you would have a perfect sphere. But that is not the case. What we have is 60 of those. 60 small geometries. So what we have is a polyhedron kind of structure. This is important for you to understand. Otherwise, the angle that you are going to get is not you. It will be very difficult to measure that angle. Okay. Fine. So how do we calculate the angle? You see this red line here. The angle is calculated with respect to the unhybridized p orbital. So that is why I have drawn this this line here. Okay. And now you will have the angle between this the pentagon or hexagon, whatever you have here, and the unhybridized p orbital that you have. So with respect to that, if you calculate the angle theta, that is what is the angle which must be between 109.5 degrees and 90 degree, which is the case for graphite. So this angle is now between the geometries of graphite and that of of diamond. Okay, fine. So this red line, that vector that I have drawn along the pi orbital, this unhybridized p orbital, we call it pi orbital. So this particular vector is known as the pi orbital axis vector, or POAV. Okay, and this basically the pi orbital axis vector is what helps us calculate the curvature of any given carbon molecule. Okay, fine. Now when this value theta, okay, so this theta, by the way, is also called theta sigma pi, because this is the angle between the sigma type bonds and the pi type bond. Okay, so this is also called theta sigma pi. So this theta sigma pi will be 90 in the case of graphite, and it is going to be 109.5 in the case of pyramid shaped structure, or in the case of sp3 hybridization. And of course, in the case of anything which has sp2+n type hybridization, the hybridization between sp2 and sp3, then your angle is going to be between sp2 and sp3. Okay, so this is basically, this angle is known as the angle of pyramidalization. Okay, what is pyramidalization? Because you had a plane. Why do we call it pyramidalization? Because you had a flat structure and now you're going towards the pyramid, right? So at some point you have the pyramid, but now you're going towards it. So that is why it is called the angle of pyramidalization. And this angle, by the way, often is calculated as theta sigma pi minus 90. But you know, this is the angle that we calculate. Why do we say minus 90? There is no specific reason, just gives you slightly smaller values which are easier to understand. When in that case, if you call theta sigma pi minus 90 as the angle of pyramidalization, in that case it will be 0 for graphite and 19.5 for diamond. Okay, but in this lecture, I'm going to use the overall value of theta sigma pi rather than rather than using the angle of pyramidalization, which is theta sigma pi minus 90.
Okay, so in the case of C60, because this is the example we started with, so in the case of C60, the value of theta sigma pi is 101.6 degrees. Okay, so theta sigma pi minus 90 will be 11.6 degrees. And this, if you back calculate from here, then you're going to get the value SP 2.28 for the hybridization. Okay, now in this particular diagram, this diagram or similar diagrams, we are also going to encounter when we talk about carbon allotropes in general. But right now, if you see this triangle, if I make a triangle where I have sp type structures, sp2 type structures, and sp3 type. So now you know what are the primary or representative examples of each one of them. Well, sp type carbide, sp2 graphite, and sp3 diamond. Okay, and we know the geometries of each one of them. Okay. Now, if you see between diamond and graphite, that is where you have all of these fullerene-like structures. So these are all the structures with sp2 plus n type hybridization. Okay. What is very interesting is that also their properties are between, the properties of sp2 and sp3 type carbon materials. For example, diamond is an insulator, graphite is an electrical conductor, but fullerenes are, most of them are semiconductors. So their properties are also kind of in between the two type of geometries. Because after all, properties are defined by the crystal structure at a larger scale, and the availability of electron, for example, for conducting for electricity, but also when it comes to thermal properties, many other properties, the free electron, magnetic properties, the free electron plays an important role. So the properties of these materials, the fullerenes, also are in between sp2 and sp3. Now, what will happen if you keep on increasing the curvature, or if you keep on increasing the angle of pyramidalization? So, let's say in the case of C60, you have 11.6. Anything below 11.6 is also possible. So, if you have little bit of curvature after graphite, you can have a sheet which is more like a tube. So it does not have so much curvature that it converts into a sphere, but it can have a little bit of curvature. So it will be some sort of curved carbon structure. Maybe it is just a kind of a wavy sheet. Any random shape. You can have this kind of random shape. You can have little bit less, little bit more curvature. Those kind of structures are possible. However, when the curvature increases a lot, then at some point your fullerene-like structures, they collapse into sp3 type structures. So this again does not physically happen, or experimentally you will not see that you keep on decreasing the size of the fullerene and then you get diamonds. It does not happen experimentally, but theoretically the structure cannot withstand more than a certain curvature. Then having diamond-like geometry will be more stable for it. So what we call it is this structural collapse at some point when you're so that is why it is people have observed very small fullerene-like structures down to C20, but if you go even further, smaller and smaller, then rather diamond-like geometry will be preferred, which will be thermodynamically more stable for that given carbon molecule. Okay, so from this diagram now you can also figure out if there should be any possible carbon structures between sp and sp2. So if there is something between sp2 and 3, there should be also something between sp and sp2, or there is at least a possibility. And in fact, many such carbon allotropes or structures have been proposed. And they also are, some of them are hypothetical compounds and some of them are, they have been experimentally observed as well. Okay, so basically this kind of classification, this kind of chart tells you that there is a possibility of finding so many different types of structures in carbons. And now all of these structures basically are found in bulk carbons. All of them are found in bulk carbons, and that is why sometimes when you have bulk carbons which are physically amorphous, it is really difficult to point out what kind of hybridization states do they have, because they may actually contain smaller structural units of different types of hybridization. And that is why their overall, if you see the bond lengths in those carbon materials, they will have a Gaussian distribution. They will be of all kinds of bond lengths will be there. If there is a certain material, if you keep on heating that material, somehow you can induce more sp2 hybridization. In that case, you will see that, okay, now the sp2 type bond length, the fraction of that is increasing, but you will still always have some bond lengths which do not fall, which are not exactly that of the diamond or that of the of graphite. Okay, so the point is that all of these sp2 plus n type carbon structures, we call them curved carbon structure. At least in this course, I'm going to use this terminology, curved carbon, because these carbon structures, they often have physically certain curvature, and they will make some very interesting carbon materials. For example, non-graphitizing carbon materials. This is going to form a large section of this course. Okay. Fine. Now I'll give you a few little mathematical exercises for you to do. Okay. First of all, find out the number of pentagons in different types of fullerenes. At least the completely closed fullerenes. So if you take C60, C70, or you go down to C20, try to find out how many pentagons will it require to form that kind of sphere. Okay. So this is exercise number 1. What you can also do is now you take different angles of pyramidalization and try to back calculate the hybridization states. What you can also do is, well, if you already have all these calculations, you can write a little code where you can, just enter the value of hybridization and then back calculate the geometry, or the other way around. Okay. Fine. So now I'll tell you a few options for further reading. So this angle of pyramidalization, the credit goes to R.C. Haddon. He has multiple publications on this topic. I have mentioned 2 publications, but you can also, you can simply search for pi orbital axis vector and then Haddon, and then you can actually find a number of publications from there. Also in these publications, the chemical reactivity of fullerenes has been, have been associated, and based on the hybridization states, now the chemical reactivity can also be back calculated. Okay. Also, there are some other NPTEL lectures. I had also mentioned in one of the previous lectures that I'll tell you a few things about where can you learn more about quantum mechanics and orbitals. So there are a couple of lectures that I have mentioned. Of course, there may be some other lectures as well where you can learn more about quantum mechanics and the shapes of orbitals and how do we derive the orbital shapes. Okay.
Now, I told you that in the case of manufacturing materials, we often back calculate the hybridization using the geometry of a certain crystal or a certain structure. Well, yes, but it is not as straightforward. It's not just a mathematical numerical average of sp2 and 3 type of hybridizations. So I will give you an example in the case of C60. The angle, in fact, we have also discussed this in the class. The 101.6 degrees is your is the theta sigma pi. This is your theta sigma pi. However, the hybridization is sp 2.28. So from here itself, you can probably guess that the hybridization is not just a direct average. Okay. So then, how do we calculate these things? Okay. This is done using some computational methods, and typically in quantum chemistry courses you can find more details about these methods, but one very common method is known as the Huckel molecular orbital theory. Now, I will not be going into the details of the Huckel theory because number 1, it's beyond the scope of this course, and number 2, I'm personally not an expert in this area. However, you can find various NPTEL lectures or any other resources for understanding the Huckel theory. What I'm going to do here is I'm going to explain it just in the context of curved carbon structures. So what I'm going to just write down the general expressions for sp2, sp3 and sp2+n type of hybrid orbitals. What do I mean by that? Typically, hybrid orbitals are written as linear combinations of atomic orbitals. So hybrid orbitals are your molecular orbitals. So what we can do is we write them, and this is what we do in the Huckel molecular orbital theory. We write these orbitals as a linear combination of the atomic orbitals that are participating in that in the formation of that molecular orbital. Now when we write that, so specifically in the case of carbon, what we do is we write down the contributions of s-type orbitals and also the p-type orbitals. Typically, for finding out any details of the hybridization, what you do is you try to find what is the p contribution. So what is the p contribution when it comes to your sigma bonds, and what is the s contribution in your pi bonds. So that is why you will write SPN for finding the p contribution in sigma, and SMP when we are talking about the s contribution in pi bonds. Now what I'm going to do is I will draw again, as we usually do, our hybrid orbitals. Okay, so we make again this pyramid-like structure. So this is, remember, this is a general case. By general case, I mean that we can use it for sp3, sp2 both. But in the case of sp2, this orbital, hybrid orbital, let me call it chi1. So in the case of sp2, this chi1 will be your unhybridized p orbital. In the case of sp3, this is a hybrid, one of the hybrid orbitals. Okay, so chi1, chi2, chi3, and chi4, these are my four my four hybrid orbitals in a general case. And the chi1, as you can already see, so chi1 is basically, this is parallel to your pi orbital axis vector. Okay, so basically this is parallel to the pz. Okay, now what I'm going to do is I will write down the expressions. I will write down the expressions for the linear combinations of these atomic orbitals for all three cases, sp2, 3 and sp2 plus n. So the first expression is for the sp2 type hybridization. Okay, so here you can already see that your chi1 is nothing but your pz orbital itself, or the vector, the pi orbital axis vector. But the expressions for chi2, chi3 and chi4 are the ones that are calculated using the computational methods. Okay, now the expressions for sp3 type orbitals, these are the expressions. Now here in this case, because all four orbitals are hybridized, then you also have a different expression for chi1. So this is the case for sp3 type orbitals. And finally, the important one is the general case for the sp2 plus n type orbitals, 2 plus n type hybridization. Okay, so this is the general case. Now here, importantly, you will see that we have two constants, a and b, because we don't know what is the contribution. This is again, it can be any value of n because this is a general case. So here we need to just assume two constants, say a and b here, and then we write down the contributions of the orbitals in terms of a and b, and ultimately calculate the values of a and b. So this is basically was just to give you an idea of how we find out the values of n in the case of sp2 plus n. If you are further interested, I would recommend that you go through some of the computational chemistry courses. Okay.